Hello, welcome you all for discussion. Today's discussion. Earlier we have discussed how impulse, what is the condition of the maximum power generation by impulse turbine. We have discussed that when velocity ratio U by C means U is a peripheral velocity of the blade or rotor and C is a incoming velocity of the steam from nozzle to the blade. When it is approximately equal to zero point 0.5, then maximum power generation and work is done. That we have defined. So now we can draw how by drawing velocity diagram at inlet and outlet and superimposing both velocity diagram at inlet and outlet in single diagram, and how we use this diagram for the calculating power generation by steam and work done and blade efficiency, grass stage efficiency, axial thrust and tangential force. All these parameters we can calculate by using graphical method, because in turbines we have to find out what are maximum power, what are axial force, what is work done per second, what is power generation, blade efficiency, or diagram efficiency, and gross stage efficiency. All these terms are very useful from the competition point of view, whether it is a gate examination or it is a Indian engineering service examination. These are very important, and I would like to suggest you that please like and subscribe, and also share it to your friends. When you like and subscribe, it will motivate me to prepare more and more videos that will be helpful for you. Hope that you will do it. So now we will discuss how impulse turbine, because there are two types of turbines, pure impulse and pure reactions is almost impossible, and mixed one are mostly used in power generation. Mixed one means it is almost 50% reaction and 50% impulse. When there is no change in pressure while steam is moving from the blades, passage is a constant one. Passage of the steam moving over the passing over the moving blades is a fixed one. Then only velocity direction change, no pressure change will take place. Pressure change will take place only in fixed blades or nozzles. When the steam coming out from the boiler and entering into the turbine, it is passing first from the fixed blade. These are known as nozzle passage. Purpose of nozzle is to convert high pressure steam into low pressure, and it is high velocity steam. So exit from the nozzle is very high velocity steam, and when this high velocity steam will pass over the blades, then direction will change place, and due to change of direction, velocity will change of direction, impulse will change, means rate of change of momentum will occur, and due to rate of change of momentum and force will generate. So all these things how we can define by the diagram. This is we are going to discuss. It is very important, and it will make, certainly it will help you. So first we draw a blade. Take a fixed blade. Sorry, this is a moving blade. This one is a moving blade, alpha 1, and this is a beta 1, and there is a nozzle. There is a nozzle here. This one is a nozzle. From nozzle exit velocity of the steam is C1, and due to motion of the blade also, it is equal to blade steam will enter at the tip of the blade, not at the constant velocity C1 but the relative velocity CR1. And there is also component CF1, means axial component of velocity of this steam. So steam from fixed nozzle coming out with absolute velocity C1, making an angle alpha 1 here, not this angle. This is alpha 1. Alpha 1 here, not this one. This is not alpha 1. This one is alpha 1, means nozzle angle steam of the absolute velocity making an angle tangent of the blade, this one. So this is also equal to, because blade is also moving with velocity u. So this velocity component also shown here. This is a u, and whole component from here to here is a CW. This is a CW1 whirl component, means linear velocity component of the steam, which is responsible for rotation of this blade. So all these things, alpha 1 stand for the nozzle angle or angle made by the absolute velocity C1 of the steam coming out from nozzle with the tangent of the blade, and beta 1 is the angle of the tip of the blade with the tangent of the blade, angle of the tip of the blade. This is a tip of the blade and making an angle with this horizontal line, means a tangent over the blade making an angle beta 1 with this relative velocity. And CF1 is axial velocity component of this steam, and this component is responsible to move. So this is the axis of turbine, there is rotor, so along this direction steam is moving. So this component CF1 is responsible for the movement of the steam along the axis of the turbine. If this component is not there, then steam will not move along the axis of the turbine. Now this is the inlet diagram, velocity diagram. Now draw same outlet diagram. When steam after gliding over the smooth surface of the blade, it will exit with relative velocity CR1, CR2. Suffix 1 is used for the inlet, suffix 2 is used for the outlet, and vertical component will remain same if there is no any friction CF2. Now this is CR1, CR2, and absolute velocity with which steam will coming out from the exit. This is a C2, and this angle is a alpha 2, and this angle is a beta 2, and here this one is a U blade velocity, linear blade velocity, or rotor linear velocity, and this one will equal to CW2. All component we have shown here in inlet velocity triangle and outlet velocity triangle. 1 stand for inlet, suffix 1 stand for inlet, suffix 1 inlet, and 2 for exit condition. All parameters similar, you can see CF1 equal to CF2. Although here not saying visible similar, but because of the drawing, but actually if there is no any friction over this surface, then CF1 equal to CF2, and also CR1 equal to CR2, and beta 1 equal to beta 2 in case no friction. For no friction, you will find two things: CR1 equal to CR2, beta 1 equal to beta 2, and CF1 equal to CF2. So these are relative velocity. These are angle of the tip of the blade with which relative velocity strike at the blade with the horizontal, with the tangent at the tip of the blade at inlet and tangent at the tip of the blade at the outlet. This is beta 2 and this is alpha 2. Angle of the nozzle, or you can say absolute velocity making an angle with the tangent to the tip of the blade, or here you can see the alpha 2 is the angle of the velocity component, absolute velocity component leaving from the exit of the blade and making an angle with the tip, making an angle with the tangent of the blade here. This is tangent of the blade. Here we have done tangent of the blade. These are two velocity triangles at inlet and outlet. In industries and for calculation purpose, we can superimpose these two components, because we know that your peripheral velocity of the blade or peripheral velocity of the rotor remains constant for inlet and exit. That's why we can superimpose these two velocity components in single velocity component. So first let us draw these two components here. So first we have to take some suitable scale. For example, 1 centimeter equal to 50 meter per second, or 1 centimeter equal to 100 meter per second, because all the values we have to show in meter per second. So U is a constant, and same for both triangles. So we take common here U. So U is common for both velocity triangles. So let us draw first U. Taking suitable, first you take suitable scale. Draw U. We can draw a straight line. I think we have option for drawing a straight line. So draw a straight line here. Not showing. Not making. So draw first by sense and magnitude, because velocity has sense, magnitude and direction, all three values. And take angle, you know that velocity U. First we draw U and then we draw C1. How we draw C1? Take angle alpha 1 here. Take angle alpha 1 here alpha 1 here, and we know the magnitude of the steam absolute velocity C1 because it is a given how much velocity there when steam is coming out from the nozzle. So it is given according to scale. Select a length of the, suppose this is a length B and join this one from C. Take C, and this one becomes CR1. This is a CR1, and now extend this one here, and draw vertical line, join here. So this becomes CF1, BCD. So this becomes CF1, and whole component from here to here, you will say it is a CW1. It is a CW1. So you know that this one is a C1, this one is a C1, CB equal to CR1, and BD equal to CF1, and AC equal to U means blade velocity, linear blade velocity, or rotor linear velocity. You know U equal to pi d n by 50. This is generally given. N is a rotational velocity in RPM, revolution per minute. D is a diameter of the rotor. So inlet triangle now drawn. So how we draw? This is angle beta 1. And how we can draw? Because we know that if there is no friction in blade, CR1 equal to CR2, and beta 1 equal to beta 2, and CF1 equal to CF2 already you will find. So take angle beta 2, same angle we take beta 2, and draw a line. This is a beta 2, and cut same value CR1 equal to CR2. Cut same value and join line this. Join here and extend this value here. If it is A, B, C, D, E, and draw vertical line here. This is a CF2, and this value from EF, this value equal to CW2. So, and if you join this value, same you will find BF. B equal to DF. So now this component, this value equal to C2, absolute velocity at exit. All component we have drawn. This one equal to CR1 equal to CR2. Although in figure you may, because it is a freehand sketching, so you will not see that CR1 equal to CR2, but actually CR1 equal to CR2, and you will find this line is parallel to this line. B equal to DF equal to CW equal to CW1 plus CW2. Sum of the whirl component at inlet at exit. Here we have whirl component, this one from here to here, and here whirl component, this one. Here you see that you are in same but in opposite direction. So this one diagram we have drawn for the condition when there is a smooth surface, no friction. But if there is a friction, what will happen if there is a friction while steam is gliding over this surface? So in that case, CR1 is not equal to CR2, but CR2 equal to KCR1. Frictional coefficient of friction. K is a coefficient of friction, and K actually velocity coefficient. This is not a coefficient of friction, but velocity coefficient. Ratio of CR2. K equal to CR2 upon CR1. Ratio of velocity or relative velocity at exit to the inlet. This component is known as a coefficient of relative velocity. So this one is always less than 1. Generally value of K lies between 0.8 to 0.9. This value varies between 0.8 to 0.9 in actual working of the steam turbine. So next we will draw for actual case when there is not a smooth surface, some frictional losses will be there, so relative velocity CR2 will be less than CR1. So in that case, axial theft will also there. Here CF1 equals CF2, so no axial theft will take place. But when there is a friction, then CF1 will be not equal to CF2. In that case, axial theft will also develop. So let us draw second case. Case second, there is a friction. CR2 equal to KCR1 and beta 1 equal to, though angle are same, beta 1 equal to beta 2. So first we draw U A, and from here take angle alpha 1 and cut value of C1, because C1 is given by taking magnitude, and according to what scale you have taken, cut C1 because C1 is given, U is given. So this is a U, peripheral velocity or blade peripheral velocity is given U, and join this line B, this is B, and this one join here, it is equal to C, this is equal to C, and again extend here, this angle is a beta 1, and draw vertical line CD, this is a CF1, this is a CF1, this is a CF1. So now you get inlet velocity triangle, but how we draw outlet exit velocity triangle here, because we know that CR2 equal to KCR1, and K is given suppose 0.85. So 0.8 times of the CR1 you have to measure CR1, and 0.8 time of the CR1 value you have to take from CD and take angle beta 2 here. Draw a line. This is a beta 2, but beta 2 equal to beta 1, and cut value CR2 here. CR2. This is a CR2, and join this line. This is E. Join this line. This one equal to C2, and draw extend this value and horizontal line, and draw vertical line. So this is a F. This is equal to F. So now complete diagram you can see. Here you can see BE is not parallel. You can see BE is not parallel. BE is not parallel to DF. It is clearly visible that BE, because you know that CR2 is not equal to CR1. Again here you can see, and here you can see CF2. CF2 is also not equal to CF1, because this component now create axial thrust, and this angle you can see. Again, if you draw horizontal line here, you will see some angle psi, and this value you will find here equal to CF1 minus CF2, and if you see tan psi equal to CF1 minus CF2 upon CW, that is equal to CF1 minus CF2 upon CW1 plus CW1 upon, this is equal to tan psi. From this triangle BEFG, so EG upon BF equal to tan psi. So tan psi equal to CF1 minus CF2 upon CW1 plus CW2. So this is a case for the actual diagrams. There are some more complex velocity diagrams will be there, so we will discuss here. And from this diagram you can calculate all these values. Suppose you want to calculate this, because from here to here it is a CW1, and from A to F it is equal to CW2. Whole value from D to F equal to CW. So from this diagram you can calculate axial thrust, axial force, tangential force, or tangential force due to which this blade is moving, and because blades are attached with the rotor, so rotor will also move, so rotational motion will take place due to tangential component CW. So how we calculate tangential force here, because we know that tangential component CW. Suppose we want to calculate tangential force FT equal to rate of change of mass into acceleration. Acceleration is the rate of change of velocity along the axial direction. So you calculate M, because rate of change of velocity means per second how much velocity is changing in the axial direction, CW1 and plus minus CW2. Here you can see from this diagram you can see since of the CW2 means whirl component of the exit is opposite to the direction, so it is equal to M CW1 plus CW2, M into CW1 plus CW2. FT tangential component FT equal to M CW1 minus CW2, but already it is a minus sign because in exit diagram you see that it is along opposite direction. So minus minus become plus CW2, so equal to M CW. This is a tangential force. If mass is in kg and CW is in meter per second, then force equal to, because this is per second, so rate of change of velocity and into mass become rate of change of momentum. It is equal to tangential force. So this is equal to mcw Newton. mcw Newton. Suppose you want to calculate work done. So we have to remove it. How we calculate work done? W tangential equal to force per second, force into the velocity means how much blade is moving in 1 second. Means U. So M P W into U. This is a work done joule. Because this work done is per second, because velocity is U is a per second, meter per second. So work done per second is equal to power. So how calculate power? Power can be calculated by mCW into U. If we want to calculate power in kilowatts, so divided in kilo 1000, so that is equal to mCW into U upon 1000, that is equal to kilowatt power. So from this equation you can find out what is a kilowatt power developed by the turbine, and next we can find out the axial thrust here, because in actual case there is a axial thrust also. So F into A equal to mass the change of velocity per second in axial direction, that is equal to CF1 minus CF2 Newton. This is axial thrust. Due to this axial thrust, shaft will move like this. We have to provide thrust bearing to bear the shock of the axial movement of this rotor along with this shaft. So we have to maintain axial thrust as minimum as possible. So by this equation you can find out axial thrust. Now we have calculated work done, axial force, power and tangential force. Now we can calculate blade efficiency. Next one is a blade efficiency. What is the blade efficiency? Blade efficiency or diagram efficiency. Diagram efficiency means a ratio of, so we define it as NB, ratio of work done by the blade upon the kinetic energy entering per second to the blade. Ratio of work done by the blade to the kinetic energy entering to the blade per second. This is known as a blade efficiency. So already we have calculated work done equal to MUCW upon kinetic energy entering per second 1 by 2 into MC1 square. So you remove this one, so equal to 2UCW upon C1 square. C1 is initial velocity, so this is a blade efficiency, NB equal to 2UCW upon C1 square. This is a dimensionless number. You can see denominator has a component of the square U into CW upon C1 square. This blade efficiency. Another thing that we have to define is gross stage efficiency. Let us see how we define gross stage efficiency. Can we minimize this one? Let us see. Okay. Gross stage efficiency. NGS. Gross stage efficiency. That is equal to work done by the blade while steam moving from the fixed blade to the moving blade upon the enthalpy loss of the steam while passing over the nozzle, because enthalpy drop takes place only in the nozzle. So it can be defined as a ratio of work done by the blade upon the loss of enthalpy while steam is passing over the fixed blade and moving blade, because one fixed blade that is a nozzle and one moving blade, series of one moving blade makes a one stage of the steam turbine. So while steam is passing over one stage means fixed blade to moving blade, it is performing work done by the blade upon how much enthalpy drops. For performing that work, how much enthalpy drop takes place? Generally it is enthalpy drop takes place in the nozzle. That ratio is known as a gross stage efficiency. So we can define here because work done already we have calculated M into CW into U upon delta HS per kg. We can also calculate per kg because at delta HS we have taken for 1 kg, so we can take per kg, not for the whole mass. This delta H we have taken for the per kg of steam, so we have to remove M, that is equal to CW into U upon delta HS. We can manipulate because here we have taken for the whole mass of the steam, but here delta S means enthalpy draft takes place while steam is passing over the fixed blade and moving blade. We have taken for per kg, so we have to take work done by the steam per kg, that is a CW into delta H, so that we can say dividing CWU upon C1 square into C1 square upon delta HS. So already we have calculated NB equal to 2U CW upon C1 square. 2U CW upon C1 square. So multiplying by 2 CWU upon C1 square into C1 square by 2 into delta HS. You can see two components here. One is this one and one is this one. This one is known as a stage efficiency, blade efficiency, nozzle efficiency. This is a nozzle efficiency. This one is a nozzle efficiency NN, and this one already we have calculated. This is a blade efficiency. So this gross stage efficiency is the product of nozzle efficiency and blade efficiency. This is a very important term. NGS, you can see NGS, gross stage efficiency, is equal to product of blade efficiency into nozzle efficiency. This one starting in the start of the nozzle, we have defined the ratio of kinetic energy, increase in kinetic energy of the steam to the loss of due to drop of enthalpy. This ratio is known as a nozzle efficiency. And already we have defined what is blade efficiency, 2UCW upon C1 square, you see here. So this product is known as a gross stage efficiency. So we will solve some question in next lecture, and I think this discussion certainly will enhance your understanding about how impulse turbine works and how velocity diagram at inlet and outlet can be superimposed in one, and by this superimposed velocity diagram we can find different parameters which define performance of the steam turbine. Thank you for watching my video lecture, and if you think please subscribe and share it to your friends and like it also, and make a comment for further improvement, or if you want to particularly get lecture on a particular topic, then please ask me. I will prepare topic and we will solve certainly some question, because without solving question you can't have permanent understanding, and solving question is the ultimate aim of the subject, not theory but solving question. So thank you very much for watching. Have a nice day.